Hello there. We have several problems today that we like to solve. Some of these problems can be solved by using Gauss's law, and some may not be. Okay, so let's uh, let's look at all of them today. Okay, so here is a very simple one. This problem you can solve without using Gauss's law. For instance, this problem say A. So what's the electric field here if this is positively charged with uniform charge density? So method 1 will be just do minus L over 2, L over 2, and a distance S, that point P. So find the electric field using length L, right? So this will be a function of length L. At point P will be function of length L and the distance S. It will turn like this. So how do I get the electric field in this case? We just so electric field, and I would do this. I've done this similar problem before, so you want to check out previous video, that's fine. So at point P, which is a function of S, will be limit L goes to infinity, because both sides will go to infinity. And so the question is how to find for finite, and that you can do by using, maybe this is the z-axis and maybe this is the x-axis. Just place this point on the x-axis. Symmetry you can place anywhere along the in xy plane, and at some point z you pick a small element dz has charge lambda dz, and from this charge at this point the electric field is in that way. So you figure out dE at P, and then you integrate it. That d at P in terms of dz, and then you integrate minus L over 2 to L over 2, and you should get that. Okay, that's a lot of work, and it's not necessary to do this work if you do it Gauss's law. So this is like a method. This method will always work, symmetry or no symmetry. You can set up the integral, and that's the fundamental definition of static electric field. So this is coming using electric field from any small charge is how much the charge there is. This is the source charge over 4 pi epsilon naught, and then you have a u hat from the charge from dq to the point P. Then the distance between them is squared, right? So r squared. R is the distance between where dp is and dq is and the point P is. So this is the fundamental electric field, and this is a unit vector. Okay, so let's do another method, the Gauss's law method. First, to apply Gauss's law method to find these things, we need to make sure that it has a symmetry. This one has a cylindrical symmetry. For instance, this is uniform, so this is the z-axis. So this is the z-axis. So it goes all the way entire z-axis. So this point P, no matter where it is, as long as they're all same distance from the axis, they have all same electric field. So this is point P, and all the points which is same distance S have the same axis, right? So if you remember Gauss's law is actually electric field flux n hat dA on this surface is a closed surface equals Q enclosed over epsilon naught. So I can, if S allows E to come out, so the electric field may be some magnitude E and it has its own direction. So this is a unit vector in the direction of electric field. If that happens, then this electric field will come out, and in the surface you have a E hat dot n hat dA Q inc over epsilon naught. And so you can see I can divide by this. This is just the area. I can divide by this and I get the magnitude of the electric field, right? That's the Gauss's law. This is the way Gauss's law problem is solved. So here, if you see very carefully, I need to know what this S is that will allow that. This is the very specific S will allow that. So I need to think of a closed surface. Over here, we can think of a surface made of these points all the way around. So this is a surface, not full cylinder, just the outside surface of the cylinder. But this is not closed, right? So to close it, I will let me use another ink color. So to close it, I will have that surface and the bottom part also. Then it's a closed surface. So actually made up of let's call it S1, let's call this S2, S3. So my S is made up of S1 plus S2 plus S3. And let's examine what this integral will be. This integral will be on S1 plus S2 plus S3, and then this charge is well, let's call this height h. Okay, so this will be the wire is lambda per unit length, so lambda h. So lambda h will be enclosed over epsilon naught. So now I need to somehow process these integrals in this fashion, right? So notice that on this surface, if I go at any point, electric field, if say this is positive, charge is positive, okay? So electric field is out. Anywhere electric field is outward at that point. And the normal is also outward. Normal is always from inside the surface to outside. In Gauss's law, the notation for normal is from inside to outside. So they're both in the same direction. And so if I do this, this will just be magnitude of electric field. And we already talked the magnetic at distance s, magnetic field should have same thing. So this becomes E, comes out, and then this becomes just the area of this surface. Just becomes the area of this surface. So E comes out, and this. So this thing is simply becomes E times 2 pi S times H. How about this guy? Well, if I look at any point of this, because the wire is that, electric field is this way, electric field, but the normal is that way, and so their dot product n hat is 0 at every point of this surface. So this will be 0 dA and this will be also 0 dA. So these guys will be 0, and so from here we get electric field magnitude is H cancels out from both sides, should cancel out because that was arbitrary, at a lambda over 2 pi epsilon naught s. S is the distance from the wire. So this gives the magnitude, and so if I want to write down the vector, the electric field vector is lambda, and the u hat is just the radially outward, lambda u hat over 2 pi epsilon naught s. Notice that notice very important, this is not distance squared, right? The wire is infinite, so that's actually ate up one of the distances from the denominator. So this is actually going 1 over distance rather than 1 over distance square. That's very important. It has important consequences. So just to recap, our closed surface, closed so-called Gaussian surface is made up of 3 parts, and in each part I know which way the electric field is pointed and which way the normal is pointed. And in this one, electric field and normal are pointed in the same direction, and their electric field has the same magnitude at all points of the surface. So it nicely becomes this way. On this and this, electric field is normal to these parts of the surface, and so they give you 0 contribution. And so this is this was much easier way to do it, but there's a cost to it. More advanced mathematical knowledge is required to handle this, right? Versus this one, you just need to set it up and do the integral over here. Actually, there is and then take the limit. Okay, now for a wire, it actually is a very I could have done both ways, but how about if I have infinite cylinder with uniform density? Now there the integral becomes really horrible, okay? And Gauss's law provides a much better way and a straightforward way of doing it. So I'm going to erase this and let me do this problem. So let's call it B. I'm going to do B, okay? Okay, so to do B, let's do the P out first. Was the electric field here? Now this actually is almost the same as that, because we have a infinite wire, and if you know, we really didn't make use of the dimension of the wire, how thick the wire was. This point was outside, so this will exactly be like that. Okay, let's see how that will be. So we can imagine the electric field has to be pointed away from the axis. So this is the z-axis, because that's the only way it can be. Or you can make logic just like over there. You can say I have this, maybe a wire here, say distance z over here, and then distance z down here. These will produce electric fields exactly in that direction, and when the add them, so this will be the electric field, net electric field. So it all in that direction. The same argument would have made over there. I forgot to make that argument over there. The electric field will be pointed in this direction away. So if the radially out, let's say this is some x-axis, just for the, and this is the z-axis, then this will be pointed towards the x-axis, assuming this is positive charge. Otherwise it will point negative. If this is negative, this will point in the opposite direction, but we just assume it's a positive for reference. Okay, so it's pointed in that direction, and So if you look at cylindrical system, this pointed in the radial part of the cylindrical coordinate, right? So this is the electric field pointed in that direction, and there is no difference between any of these points, because this thing goes all the way, the entire cylinder goes infinitely. So there's no difference between any z points. Exactly same argument is over there, and so I can imagine a cylinder just like cylindrical surface as before. So this is the cylindrical surface, not cylinder but cylindrical surface, this only outside of it. So all these points, all these outside points has there's bisymmetry. So let's call it surface S1, and then you have the top part, I'm going to call surface S2, and the bottom part we're calling S3. So S1 plus S Gaussian S, which is supposed to be closed surface, will be summation of these two, the union of these surfaces, right? Okay, so at each, for S1, in S1 what we find is electric field is parallel to the normal which is coming out from inside. So if electric field is that way, electric field that way, the normal is that way, and that's the same at every point. And over here, from the same argument as before, electric field was that way, same argument like this at that point, but the normal is that way. Electric field is always pointed away because of positive lambda, and so this is electric field is perpendicular to n hat, and this is electric field is perpendicular to n hat. So once again we get E times 2 pi, and this is height is h, 2 pi, and this distance is s, 2 pi s h plus, so over this surface I got a 0, over this surface I got a 0, and it's just as before. And so we get how much charge is enclosed here. So this is the cylinder that has charge in there, cylinder of height h. So I got a pi so this radius of the cylinder is, say, capital R. So radius is capital R, which I forgot to give, pi r square h times rho. So that's the amount of charge that's got enclosed over epsilon naught. And so you can see the go away, this h goes away, and so the electric field in the magnitude, and this is the out point, and s is the s out, because we're talking about this surface, right? So that's the s out. So we have a pi r square rho over 2 pi epsilon naught s out. Of course you can cancel pi's, and you have a rho r square over 2 epsilon naught s out. And electric field is, of course, this is x direction, but any other place I can just say unit vector. So the unit vector coming out, so this is rho r square over 2 epsilon naught s out, and that's a u hat. U hat is radial cylindrical unit vector. So this is E at out. So this was a very simple, right? That's just E out. How about a point inside? And that's the one let's do. That's going to be more interesting. Okay, so using the same cylindrical argument, we can say that the same distance you are, all of this will have same electric field. So I can imagine this surface that completely lives inside this this plus lambda, and you can see it's made up of S2, S3. So this is my S1, and this is my S2, and this is my S3. So S is made of S1 plus S2 plus S3, and it's kind of similarly at any point of this, electric field is pointed this way, away from this, and then normal is pointed that way. So this gives me no contribution. Similarly, no contribution from the bottom part. But over here, just for drawing, look at the corner here along the x-axis, is pointed that way, E is pointed that way, and normal is pointed that way. So it's going to be the same way. But this cylinder now is this cylinder integration over S1 gives me this is the E dot n hat dA. This gives me E times 2 pi S in, and this is the height, say h, and this gives me 0, and this gives me 0. So S of this integral gives me just this, E times 2 pi E, it's going to call it E in S in H. How much charge is enclosed? Well, this is the volume, so the Q enclosed will be the volume of this times rho, right? Rho times the volume. So rho times the volume will be pi S in square H. So that's what is. So this should equal, equating this to, equating integral to this rho times pi S in square H or epsilon naught. This is the Gauss's law. So this is from Gauss's law, and you can see the H cancels out, and one of the S in cancels out, and the pi cancelled out. So E in is simply actually increases as you go out linearly. Rho over 2 epsilon naught times S in, and you can see E in vector is rho over 2 epsilon naught S in U hat, and this U hat is radially outward vector. This is the unit vector radially outward from cylinder's axis. Okay, so this is these are two really typical problems in Gauss's law. So I wanted to actually address another problem. This is the C. I want to address like this problem, and then D is something that you can't use Gauss here. But C is a very clever thing, okay? And okay, so I'm going to come back and do C. So let's do C here. This is actually a very important problem. It shows up a lot in the problem, you know, in tests and contests. They give you the answer to this. They may not give you the answer to this also, but they say, okay, if I have two wires parallel to each other, it could be cylinders also, you know, and maybe they have a equal and opposite charge densities, and there is a point P in the somewhere there. It's a distance S plus from here and distance S minus from here. So what's the electric field is going to be like here? Well, the charge is infinite, so you can't put it over here. This is if you try to do any other way, you can say, okay, I got lambda here minus lambda here, and then I use my Coulomb's law. Not going to work. Okay, so you can use electric field of multiple charges. If electric field of two charges, how do you get electric field? Two charges at point P is electric field at point P from charge 1 plus electric field vector at point P from charge 2. So this is called superposition principle. And this is very important principle of electric field, because electric field, if you look at the electric field from any charge, electric from, say, from charge Q at some point P is charge Q over 4 pi epsilon naught r square u hat, right? So it is a linear in Q. So if I have a whole bunch of Q's, I just gonna have to I can just add them up vectorially. Okay, and so applying the superposition principle, you'll have a plus using this formula. You will have electric field from, say, let's call it from plus the entire thing as a vector like that, and then you'll have from this entire thing electric field minus also in that direction, because you can see the lambda minus will flip the u hat, right? So let's call this u hat this direction. Maybe this is x axis or something, so u hat will be I hat. All right, so picking x axis that direction. So you are going to get E at P is going to be lambda I hat over 2 pi epsilon naught S plus, then you go plus minus lambda I hat, okay, lambda I hat 2 pi minus plus, actually the same direction, 2 pi epsilon naught S minus, and so they're going to add, and then I have lambda is value is same, one is a plus lambda, one is a minus lambda, okay, and so I'm going to get this along the I hat direction, 1 over S plus 1 over S minus. So it's very simple. Once you use the superposition principle, the answer is this is the answer. Okay, so the last one I want to do D, that you can get carried away with applications of Gauss's law, but then Gauss requires symmetry arguments that we went through in choosing the surface properly, okay? But if you don't have a symmetric situation, then the Gauss's law will not be very useful in getting the electric field. So it still applies, it's a Gauss's law as a law applies to any arbitrary surface. However, in order to get the electric field formula from it, you need some additional information about the electric field and the surface. And so there's a choice of surface and there's a symmetry argument. And you can go to my website, and there is much more argument that you can, or you can read your textbook, a good textbook, and then they will go through the symmetry arguments, okay, in more detail. Let me try to address problem with things like D and how you can do it. Okay, so like here, if you had a cylinder, and this is infinite cylinder, so you would think this should be Gauss law apply, but but suppose this part of the cylinder, this part was all positive, maybe this was all positive, and the other part was negative. Then you can't use that argument. Then you can't say that. Then you can't say that electric field here, E at say point P1 is the same as electric field at point E at point 2. You can't say this, okay? These are not the same, and so the whole argument will fall apart, and you can't pull electric field out of the integral. So this is Gauss's law still applies over here. You can see that if they were the same density, then the net charge enclosed will be 0 here, not some value. Already you can see the difference, but still the Gauss's law will apply, but you can't really find the electric field formula from it. So you really have to do the integral, and this doing the integral for this is really hard. Another situation is, instead of all through here same charge density, you have half of the wire, like over here, is a plus lambda, and other half is minus lambda, and right in the middle you want the electric field over here. And so maybe there is a little gap, or you put a non-conducting material over here, so maybe very thin non-conducting material, so you don't have to worry about it. And you want over here, what can you do? Again, if you try to say that, okay, how about can I use Gauss's law on this surface? Clearly not going to work, because electric field here is not the same as electric field here. These are not the same electric field. There's no cylindrical symmetry here. So how do you do it? Well, you only have one recourse. You can just do like this. You can find the electric field of this guy and find the electric field of this guy at this point. So how do you find the electric field of this guy? Well, let's call this z-axis, and let's call this x-axis, and let's put over here the point. So this is a dz at distance at z. So this point's coordinate is 0, z, and this point's coordinate is let's call this s, right? S0, we'll call it x, and let's call it z prime, because this is the source and this is the field, x0. So this x is actually equal to s for us. I'll just put x there, and we need this distance. So electric field from there is dE from this is in that direction. So dE will simply be how much charge there is. Well, this is lambda dz prime, and then I have a 4 pi epsilon naught. And what's the distance? Distance is going to be z x square plus z prime square, distance squared. And then what's the unit vector? Unit vector is from here to there, right? From the source to the field. So x minus 0 I hat, x minus 0 I hat, 0 minus z k hat, and then the length of this will be x square plus z square square root z prime square, z prime square, z prime. So this whole thing is lambda over 4 pi epsilon naught dz prime over x square plus z prime square 3/2 and x I hat minus z prime k hat. Now you have to integrate 1 from 0 to so the E plus vector from this plus side, from that side, let's call it E plus. The other is E minus, that's from the bottom part. This will be lambda over 4 pi epsilon naught 0 to infinity dz prime x I hat minus z prime k hat over x square plus z prime square 3/2, and the other one will be minus lambda over 4 pi epsilon naught, and we got 0 to, this one is minus infinity to 0 dz prime, and you're going to have same type of thing, right? X I hat minus z prime k hat over x square plus z prime square 3/2, and then E will be just E from the plus charges plus E from the minus charges. So you just have to add this up. Now, how do you do these kinds of integrals? Well, there are simplifications you can make. For instance, you can pull the x out from all of these. So if you pull the x out, then this integral turns into x square, and this, maybe this turns into u, this turns into u, and this turns into 1 u square. And so this is simple integral, and you can actually do it. So these integrals, I'll show you a website that you can make use of. And so here is a website. I am going to type in here. Hopefully you can remember. So this is like a Wolfram alpha. If you go there, that's the website I go, and you can actually type in integrals. So I want to integrate. So over here is 1 plus u squared 3/2. Let's say I want to integrate that. So I'll say integrate. It understands. So 1 over 1 plus u hat square to the power 3/2. So I want to integrate. I will have a constant later on. If you wanted to put a limit also, it will take a limit also. And see, it gives this answer. And you can do the limit 0 to infinity. In the 0, it goes to 0. And similarly, if you want to do it like u over this, it will do that integral also. Okay, or you can do it by hand. I sometimes enjoy doing the integrals by hand, but if I'm in a hurry, I can just use this website. Okay, hopefully you can complete this. I'm not going to do more of this. Probably already very long video because several problems we discussed today. If you like this, please subscribe and maybe hit a like button. Talk to you in another video. Bye.